Get out of here. Stop. Oh, darn. Why can't anybody... Manage issue settings on a lot of people. Okay. I'm assuming everyone can hear me, but the problem is that nobody's on the actual chat. The YouTube page. Okay. But nobody wants to talk. Huh. That's weird. There we go. We have a bear named Dylan, who I can't hear or see. Dylan, do you have a mic? Not yet. All right, let me see if I can open up like some kind of chat or something. Oh, there's a chat on the side. Okay. Dylan does not have a mic. It's sad. I'm going to be talking to myself the entire hangout. This is going to be awful. We're not going to learn anything. Okay. Well. Let's see. Yeah, that's the link to call. All right. And I have 5 viewers. Interesting. Dylan, please have a mic. I can't. I can't be the only one on this hangout talking. I'm not good at just teaching people. This makes no sense. No, that's it. Okay. Let me see if I can invite some more people on here. There we go. We have somebody else also with no mic. David, if you can turn on your mic, that'd be fantastic. And Dylan, you too. If it's possible. Maybe I have... Why are you muted? There we go. We got somebody else. Terrence, hello. Can you hear me? Ah, okay. Maybe I have this off.
Yeah, I can hear you.
There we go. All right, we got somebody.
All right.
I might have people muted on accident.
Okay.
All right, Dylan's got the chat on. I don't think David has a mic, I'm going to be honest. Ah, okay, cool. All right, so, and then Dylan, let's see what's going on with Dylan. On the YouTube channel, there's a chat. Okay. Sweet. So everyone can hear me. Cool. All right, so how are you guys?
Doing fine. How about yourself?
You know, same old, same old. All right, so let me move this over here. There we go, Johnny. Hello, Johnny.
Hello.
What's going on? Are you at like Starbucks?
All night study.
Oh, nice. That is pretty awesome. There we go.
Type on this.
You can. There's a text on the side, right? So we can chat via Hangouts. There's also a YouTube. Since this is also broadcasting to YouTube, there's a YouTube chat that goes through, but I can't see it.
Okay. You can see this chat though.
Yeah, I can see that chat.
I'll probably stick to that then.
Yeah. Like usually what I do is like I kind of go over like everything that was discussed in class, and then if anybody's watching it before the test, then they can see what we were discussing and whatnot. So yeah, that's pretty much it. I'm actually trying to go over some summations because I am awful at summations before the call started. So we got Ravi. Hello, Ravi. All right. So where do you guys want to start? Do you guys have like something in particular that you guys want to discuss, or is it more like you just want to go over like everything in general, or just go over the exam like point by point? Oh no, Johnny, you're muted. Point by point is good with me. Okay, cool. Sweet. So, I don't got a mic, my bad, man. No real preference for me. I won't be here too long. I'll probably rewatch this tomorrow after work. All right, makes sense. Okay, so if I'm going to be honest, Andrew, hello. Yay, somebody else with the mic. That way I'm not talking by myself. Let's see. Section. I don't care. Okay. So one thing I like to do is screen share. Okay. So usually I have like a document up, that way I can write. Hello 1111.
What's up?
Totally not a robot. There's no zeros in there. I think we're okay.
Yeah.
So if I'm going to be honest, like I am really bad with summations. So I would really like to go over that because the algebra just like gets on my nerves and whatnot. So one of the first things that he has is it's something like this. It's two summations. Hold on. And there we go. So it has this, and then one of them is to n, and then it's I equals 0, and then the other one's j equals 0. No, j equals 1, and then it's, hold on, I forgot what it was. There we go. N plus I to the n. Okay. n plus I to the n, right? So I honestly don't remember all of the rules. I do know that you can pull constants. So anything that's not a j or an I in this example, you can pull forward, but there are certain rules that you have to follow when you do that. In this case, right, since we have j's, and we're trying to add up all the j's, but there are no j's, so that's just 1. So it just comes out to, I believe it's n plus I, because you can, no, I'm sorry, it comes out to I equals 0 of n, and then you can pull out the n through, and then you can make it n to the n plus I, if I'm not mistaken. Right?
Yep.
Okay. Right. And then what you do with that, since we have an I in here, we want to isolate that I, and it can be its own thing. So we can do I equals 0 to n, and that would be, let's see, because we would have to, maybe 2n plus I equals 0 to n of in. Right? That's valid, right?
Isn't it n squared?
Oh, I'm sorry. That's totally right. N squared. See, whenever you think about summations, I always think add. So n squared. Okay. And then, since we have the I isolated, that's going to be, we can pull the n out and then bring it to the 4, right? And then that I is going to be n plus 1 over 2. Because like there's a certain formula for I and n and whatnot. So that becomes times n plus, and this one's the n squared one, which has its own formula, which I completely forgot.
Don't you just pull it out because it's not an I?
Oh, that's right. No, no, wait. Yeah. Okay.
So is it like n cubed?
If you're pulling it out, it would be,
Fold the left side summation because it'll be I to n of 1, which will be n.
wait. So pull the left side, so it'd be I to n of 1. Okay. Yeah. Okay. Yeah. All right. So it comes out to n cubed. That doesn't make sense. You're right. Because you can pull out any constant that's on I. See, this is why I'm really bad at this. Okay. And then from this point, you just do some algebra and then you're done. Right? So, n times n squared plus 1, that's n squared plus n over 2 times n times n plus n is going to be n cubed plus n squared over 2 plus n cubed. Right?
Mm-hmm.
Okay. And we can do 2n to make it simpler, because we're only doing 1. That would be 2n cubed plus n cubed plus n squared, which comes out to 3n cubed plus n squared. Let me know if I'm wrong.
Still have to put it over 2.
No, wait. Oh, yeah, that's right. I do have to put it over 2. Okay, so yeah, that makes sense. I was trying to do that half thing in another example. Okay, that makes sense. And we're done, right?
I think so.
Yeah.
You want to look at the chat? Some people are suggesting.
Ooh, n squared b minus a plus 1 is changing. So for the first time, I thought it would be something like n. For the first term, I thought it would be something like n squared plus n. n plus 1. Yeah, I think so. Okay. Sounds about right. This is going to be fun, this chat. Okay. So yeah, I think this is not going to be a necessary question on the exam. Has anybody taken Sumansky before?
Yeah, I have a feeling he's gonna have the geometric thing on there,
Yeah,
where the denominator gets bigger and bigger.
that is true.
He always does like that little, like he thinks it's like super smart, quirky thing, and he'll put that on the exam.
Yeah, I had him for discrete, so it was lots of fun for discrete. So he does have. I do have it here. It was analysis with summations. At the bottom. And that one goes from 3 to the I. Okay. So on the geometric series, it's going to be this. Number from previous slide, and the I. Ooh, lots of people in the chat. Hold on. There we go. Yeah, discrete. Okay. So yeah, since most of us have him for discrete, I'm pretty sure we know how his test is going to be. The one thing that I got from discrete is that it's not necessarily straightforward, and he likes to combine like questions. So especially since there's only going to be 5 questions on it, that's what I'm really worried about, because he'll have a question like this with a like something that we have to solve for a geometric series, and that will lead us to another thing, you know, on that same question. So with the geometric series, like we're doing, what exactly are we doing? Am I talking to Andrew right now?
Yeah, let's go up on the slide a little bit, and then we'll just look at the initial problem, and then we'll just try to work it through.
Okay. So there we go. All right. So there's an help us nail down our big O. 20 times 4 or 5 notes is like that too. Okay. I'm looking at some code, figure out what the summations would be, and then reduce them. Yeah, that's totally true, David. Like, so we'll look at some. It's probably going to be something like this, and we'll have to find out the sum, which will be a geometric sum, and then we would solve it like that. We would have basically what we'd have to do is identify a geometric sum of some kind. My prediction. Hello, Bradley. And that's about it. Okay, so what about this one? Info. Wow. Okay, so one thing that when I was going through these notes, when you're doing a for loop, it's very easy to find the summation for it, because what you can do is you just put, you know, whatever value that you have, you're increasing it by 1 each time, right? You put the middle of the for loop on top, and then you put the I equals 1 on the bottom, and you're done. But with a while loop, what would be a good approach for that? Because you're doing j equals j over 3, and while I equals 0. Because, okay, so we're doing the while I equals 0 because it's like greater than or equal to 1, if I'm not mistaken. Right. And we're putting both of those in there. It's I to the I. And it's an infinite loop because it ends when, how many times is the x plus plus statement executed? Okay, so this is our upper bound to help us nail down big O. Okay. So with the geometric series, let s be that. 3 to the I. Okay. All I did here is multiply by 1/3. Therefore, s is 3n over 2. Okay, how do you do that? S equals s minus 3. For our function O of n, which is our spreading result. See, this is what gets me confused because he puts like all this. He gets fancy, and then I'm like, I would rather have everything straightforward and be done with it.
It is pretty straightforward.
Can you could you explain it? Because I don't know how to explain it in words. That's I guess that's the
Start of that top slide. You know, it says s equals summation of I equals 0 to infinity. That s equals. So this is what we derived from looking at the function, right? Like this is what we think the summation is.
Yeah.
So if you just write that out, just like the first couple terms, you get n plus n over 3 plus n over 9 and whatnot.
Mm-hmm.
So all you're doing is just algebraically manipulating it. So if you just divide the whole equation there by 3, you get s over 3 equals, and if you put everything over 3, it just kind of acts like it just advances 1 forward.
Okay.
So then you go down one more line there, and you do s minus s over 3.
Equals n, which gives us our ON. Right?
Right, because everything else cancels out.
Okay. Okay, yeah, okay.
But then you still have to isolate s by itself, because we're still thinking algebraically, so that bottom left line there, you have to multiply the other side by 3 over 2. So then you get s equals that.
Okay. Therefore, s equals 3n over 2. So our function of n, which is our spreading result. Okay, and then more generally speaking, when we go down, it is the sum of a to the 1 times r to the I. Okay, where that makes sense. And then we have, okay. That makes a bit more sense. All right. So he'll have like a question like that. So basically, therefore, so wait, for this one, it says, therefore, s equals a to the a sub 1 over 1 minus r. Is that any time that you're going to see a geometric sum? Something like that? Is that what he's like? He's trying to generalize it?
Yeah, but I think it's easier if you just look at the actual example, because this shit confuses me.
Yeah, like I'm not a big fan of, hey Chris, I'm not a big fan of generalizing anything. Like, for me to conceptualize things, it has to be like a foolproof example. You know what I mean?
So if you scroll up one slide there, when you're given a summation like this where the denominator is increasing, you just multiply or divide both sides by whatever that number is. So it could be like n plus n over 2 plus n over 4 plus n over 8. In that case, you would do s divided by 2 so that you can move the right side forward one.
Let's try this out. Okay, so we have a pen that doesn't work. Okay. Oh, because I'm in my eraser. Okay. So we have s equals n over, let's say, 8 to the I. Right? What we can do is we can have s over 8. We're multiplying by. No, wait. No, that meant. What did I do?
You want to expand the n over 8i first at the top, like the first 3 terms or 4 terms.
Okay. So it would be n over 8 times n over 64 times. Now, I think I made a mistake. I have to use 512? Okay.
Yeah, but at the front, you need just a n, like n plus n over 8 plus n over 64, because that's basically I to the 0.
Okay. So n
Yeah, and it's addition.
plus.
So if you have this right now,
Mhm.
the first step would be to divide everything by 8. So
Okay.
then you can, so if you write this, the second line out, it'd be n over 8 plus n over 64
Plus n over 64
plus dot dot dot.
plus n over dot 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 dot.
So if you take the left-hand side of both of those, it becomes s minus s over 8.
S minus
S over 8.
S over 8.
Yeah, because those are the two things you just expanded. And when you do that, those all cancel out except the n. You see that, right?
Okay. So what we're doing, no. One more time.
So if you have s minus s over 8, the s is n plus n over 8 plus dot dot dot, right? That first line.
Mhm.
And if you subtract s over 8, which starts with n over 8 plus n over 64 plus dot dot dot,
Everything. Okay, so everything
everything
gets
will
canceled
cancel out
out
to infinity except the n.
except the n, and then that's how I get my. That's how you get on, right?
No, not yet. So you do. So you make that equal to n, and then the next line will be
So s minus s over 8 is equal to n, correct?
right.
Okay. And then
So that's 7/8 s equals n, I guess.
s minus s over 8. Yeah. 7/8 s equals n.
Yep, and then you just multiply both sides by 8 over 7 to isolate s.
Times 8 over 7 times 8 over 7. And that comes out to 8n over 7 equals rs. And then this is our on.
Mhm.
Okay. Okay. Makes sense. Is it times or plus? No, it's plus. It's definitely plus. I was thinking something else. All right. Dylan's back. Okay. All right. So let's go back here. All right. So we have stuff like geometric series. Is there anything else that he might like ask as far as like this type of question? Because I would have it that he would probably ask something along the lines of, find out like what's the value of this, what's the runtime of, or no, what's the summation of this function, and then find this geometric series, and then find the O and runtime from this kind of style. And it would probably be like something moderately confusing, but not something that we couldn't do without knowing like what this is. You know what I mean? If that makes any sense. It didn't make any sense, did it? Okay. So, all right. So let's think. That was infinite. That was infinite in the notes. It's not infinite. And how you get the answer is different since the subtractions don't just leave the n. Okay. So.
Oh, if it's finite, then you gotta write out the
entire thing.
The end of the, what do you call it, expansion. So you get like n plus n over 8 plus dot 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 plus n over whatever the last one was.
Yeah. So
when you subtract, you have to account for that.
Yeah, because if we're doing something like this, right, where it's I equals 0 to 500, we do have to evaluate it to 500. We can't evaluate it to infinitum. Yeah, I understand. Okay. Yeah, the last one, yeah, in the notes, 3 plus 3 to the 501 over 2. Okay. Yeah, no, that makes sense. Okay, cool. So we have that. What else do we have?
Do you want to go over deletion from 2, 4 trees?
Oh yeah, definitely. What question is that? Because what I want to do is I want to just go down the list of questions that that we were given in order to study for the test.
Oh,
You know
I
what I
don't
mean?
have anything. I don't have anything specific. I was just going down my list of what I should look at.
Okay. Hold on. Let's see. I mean, we can do that unless anybody wants to object, because I was just going to go down this list.
Yeah, we can just go down the list then. We'll
Okay.
hit it eventually.
Yeah, that's true. Formal definitions of big O. Know the formal definition of big O, big omega, big beta. Okay, so now once again, correct me if I'm wrong. We have big O, right? So is f of n equals c of g of n. No, I'm sorry, not equals. Big O is less than c of g of n, right? Yeah, okay. So basically what this is telling us is that for any function that is given, right, we can find a function that is bigger than it and then define big O in that way. So for example, if we have 3n squared, right, we can derive big O by saying, okay, well, let's go ahead and go with the function 4n squared. We know that that's bigger than that, right? And then we can derive our n, you know, in such a way that we could say, let's do a +1 here to make it easy. And then let's do, I'm gonna make it super simple for myself because I've been doing a lot of math. So what we can say is like, okay, so we have this variable here, and we can be like, okay, well, at what point, because we also have to say for n is less than or equal to n naught, right? Both c and n naught are constants. So g of n is just another function that we can put in there to prove big O, and c is just a constant that we can use to derive anything. So we can literally put anything in here, and as long as we find like that point, we can prove it. So for this example, we could say that, yeah, we could say that minus n for n equals 1. So we would be like n squared darn it, I wish I figured this out better. N squared, 3n squared, 3n squared plus 1. Okay, so n squared is less than, I'm sorry, n squared is less than or equal to 1. And then if we root, n is less than or equal to 1. So that means, okay, don't forget to define n1. Thank you, Johnny. So we have n is less than or equal to 1. So what we can say from here, right, is that this value holds true, right? So the 3n squared plus 1 holds true for all values of n less than or n less than or equal to 1. No, wait, that's wrong. I did that wrong. How did I do that wrong? Because I have to do greater than or equal to, right? You can't add. Define C. Okay. See? Thanks, guys. So let's try it this way. What did I do before? It was There was an easy one that I just did yesterday. Isn't it? Yeah, it's greater than. I'm doing big theta. And I know somebody is talking, but I can't hear them because their mic is kind of there. And it's greater than. Okay. So greater than. So big O is greater than omega is the same thing. But less than for n less than or equal to n naught into which yields 3 into 3 into. Yeah, I'm coming up with things in my head, and I'm not doing well, so I should probably just stick to the regular books. And then you have big theta, which is the upper bound and lower bound of both of those things. So you're trying to find like a middle pathway. So you have f of n is greater than or equal to, I don't remember the formal definition. Let me just double check it real quick. Big theta. Yeah, it's f of O is O of g of n, and f of n is big O of g of n, and then f of n is omega of g of n. Okay, and that's what will yield theta. Okay, so theta is quite literally a mixture of both of them, or the in-between of both of them. So if we have, there we go. We have f of n, c, g of n for n less than or equal to n naught. No. Let's just do this. O of g of n, and then f of n is then equal to omega of g of n for n. Did it wrong again. And not. Right? I'm pretty sure it's always n is greater than. I think so too. Let me check. Big O light. Okay, so big O, that's greater than, and then big omega. Ah, yes, it is always greater than, except for big O, which is less than in here. So it's always, you're always looking for greater than. So you're right. So there's that. And change that there. Okay. So we have that. So let's go ahead and try something. So we have, this is the first thing that on the thing is function 1/8 n squared plus 1/8. And then we have to find O of n squared. If we're doing that, what we can say. See, so like I I had a conversation with somebody on the Facebook chat, and it's mildly, like, I understand the concept behind it, but I'm not entirely sure how accurate I should be. Because what you can technically do when you're doing this is if you're trying to find big O, you want to find any value that will make this true. So n squared plus 1/8, right, is, want to do less than, where's my thing? There it is. Less than, oh man, my thing's gone. There we go. Less than any value. So you can be like, I want like 2n squared, right? Because we know that this is probably going to be less than 2n squared. And we can put in any value for n to yield that to be true, right? So you could be like, okay, well, if n equals 1, right, let's see if this works. So we have 1 squared, 1/8 plus 1/8, that's 2/8. So we have 2/8 over here. And then we have that. And then we have 1 squared is 1 times 2 is 2. 2/8 is obviously less than 2, so therefore we've proved it. But I feel like this seems really wrong. If anybody could back me up on that, like, this doesn't seem like the proper procedure, because I feel like the way that he does it is completely different. He'll do something like 1/8 n squared plus 1/8, and then he'll do is less than or equal to 1/8 n squared. In class, he says he needs to understand how you got to that number, e.g. multiple f by n by n. Okay. Wait. Multiple f of n by n. Okay. So yeah, he'll do something like this. Like, it'd be like 1/8 n squared plus n squared, right? Actually, in the notes, he does this. Stop. Okay. So he'll do something like this. He'll be like, he wants to prove O(n) cubed, right? So you can be like, okay, the function is 3n squared plus 10 is less than or equal to 3n squared plus n squared, which is 4n squared, which is less than 4n cubed, right? Which, this is the part that I'm a bit confused with, because like I can see like through inspection that 4n squared is definitely less than 4n cubed, right? But I'm a bit troubled as to why he decided to use these values, or what he was getting at. You know what I mean? To prove n. Well, no, I understand he was trying to prove n, but it was kind of like, to prove n, then n squared 10. That n doesn't have to be 1. Okay. No. I understand that n doesn't necessarily have to be 1. But for example, maybe I'm thinking about it like, you know, I'm trying to think about it algebraically, and it's not really what's supposed to be happening. Yeah, no, it doesn't have to be n naught. N naught does not have to be 1. Yeah. He doesn't just want a random number. No, understandable. But are we trying to prove it algebraically? Where does the 4n cubed come from? The 4n cubed comes from I think what he's doing, right, is because he's trying to prove O(n) cubed, right? And we know that if that's what we're trying to look for, right, the 4n cubed is a big O of n cubed, right? Because he's dropping the constant. Is that what he's doing? No, I can't hear anybody. You might have your Johnny. You still have your mic off, so I'm not entirely. No, that's not it. I have nothing to add. Okay. Yeah. See, this is what confuses me the most, because like anytime that I look at this, like these inequalities, I just want to solve it algebraically and then be done, because you can solve for 4n squared, right? And that's where he gets the root 10 from, because if you're going for 4n squared, you can do it this way, right? So 3n squared plus 10 is less than or equal to 4n squared, right? Which is what he got from 3n squared plus n squared, which is what he invented, right, to solve the problem. So you have g of n. Okay, yeah. So this is your g of n. So that 4 is technically your c, n squared is your g of n, right? Then what we can do is subtract this 3n squared. That becomes n squared less than, or I'm sorry, greater than or equal to 10, right? Root n is less than or equal to 10. No, greater than, sorry. Greater than, right? So since we know that 4n squared is less than, definitely, than 4n cubed, right? We can just use 4n squared. If I'm not mistaken. Tell me I'm wrong. Because that's what it seems like he's going with when he's talking about this stuff. So 3 is 4n cubed. Because he told us that big O was the upper bound of the entire equation. I think he wants it broken up similar to f of n. What do you mean by like broken up similar? Like when we're doing the equation, down to 3n squared plus n squared, with f of n being n squared plus 10. Okay, no, yeah, that does make sense. But see, like, I'm just trying to conceptualize what his thought process was when he was doing this. This inequality holds because n squared plus 10 is over 10. And we see that 4n squared is less than 4n cubed, right? And so since we have the 4n cubed, that's our c, and then that's our g of n. Okay, n squared, c is 4, g of n is n cubed, and n squared is less than root 10. Okay, I think I got it. Okay, I understand. All right, so when he's doing this, right, the definition is f of n is, wait, let me see this real quick. Less than or equal to, okay, less than or equal to g of, no, c times g of n for n greater than or equal to n naught. Okay, so basically all we're trying to find are these values. And it doesn't matter what you put up here, because what you're trying to do is you're just trying to find a value here that would be less than or equal to n cubed, or your g of n. And basically you just want to find your c, your g of n, and your n naught, and then you're done. And that'll prove your statement. So you have the function 3n squared plus 10, right? That's your f of n. Is less than or equal to. And then what he did is like, okay, well, it's what I can do to make sure that I have something to compare that is equal, or I'm sorry, that is greater than this statement, is I can put 4n cubed plus, or I'm sorry, 4n squared plus n squared, right? And then we can make that, I'm sorry, 3n squared plus n squared. That equates to 4n squared. And since that equates to 4n squared, we can go ahead and solve for this equation, which comes out to this. And since we know that for 4n squared, this holds true, right? We know then, because we know that that's less than or equal to 4n cubed, yeah, we know that this is equal to 4n cubed. So that means that this holds true. This is your C, and this is your G of n. Thoughts? Questions? I don't know. I can barely hear Andrew. Hold on. Let me see if I can turn up your mic. Andrew, can you hear me? I think you are correct. Thank you, Robbie. All right. And then the same thing applies for big theta, because big theta just means the lower bound. So what you're doing is you're trying, like, let's say, for instance, if you applied the same logic, right? I'm not going to solve it because this probably doesn't work the same way, but you have 3n squared, and you wanted to make sure that your, I'm sorry, not theta, omega. You want to do your omega, and your omega is ON, like something that you know, or O1. That actually makes it easier because everything is smaller than that. So you're like, okay, well, what I want to solve for is we want to make sure that this value is bigger than, a constant value, because that's what, when you're doing omega 1, that's what you're trying to go for. So what you want to do is you want to do like, well, anything really. I mean, you could do like a 3, and then you can solve and try to find out what your n squared would be. So actually, that would totally mess me up. Actually, no, yeah, that would totally mess me up. You can't do that. Let's do. We can do 11 minus 10 minus 10. That equals 1. 3n squared over 3 over 3. N squared 1/3. Wait. N has to be smaller. Yeah? No, this is right. For n greater than or equal to. Okay, so then you root it, and you're done. N for all values greater than root 1/3. That statement holds. Yeah? Okay. And then if you wanted to do theta, it's basically taking both of those together and creating an upper bound and a lower bound. Your big O is your top level, and then your omega is your lower level. And then whatever bound that you have in between here, it's between here. And this is like, and I remember in the notes he did say something like, this is our better concept of what big O was. Yeah. This is what we saw big O established as sort of upper bound. Similarly, big omega established sort of lower bound in the same function. Both upper and lower bound will be sandwiched between f of n, g of n curves, which multiplied by some constant, of course, discovered as height bound. Okay, this is how we got our f and n sandwich and on g of n bread. Okay. Maybe this is maybe breakfast and which will be posting all of courses. Okay. Cool. So that makes sense. All right. So that seems pretty simple. I'm thinking that if he does something like this, like say for example, we have a practice exam problem. Okay, if we're going down, give a summation that represents the number of times line x plus plus is executed in the following line, so then derive its closed form, then give the order of the algorithm proving the big theta notation, prove the big theta result for the expression that you derived. Yeah, this seems like this would be a very good exam problem because it has both of the things that are combined together into one thing. So what we would have to do is we would have, I'll bring this over here to the other screen. Okay. What we'd have to do is we'd have to summate the for loop. So it would be 1, I equals 0, 2, P, and then I plus plus, so that's 1. Okay. And then P equals math pow 3 to the n. So P equals 3 to the n. And then whatever that n is. Oh, this is a pain in the ass. Okay. So we would actually have, unless I'm doing it wrong, we'd actually have I equals 0, 3 to the n for 1. And if we're doing, there's something, so if we're doing I equals 0, there's something special about it. I forgot what it was. It was doing 3 to the 0. 3 to the 0 is 1, right? Yeah. It's 3. Yeah, 3 to 0 is 1. B times A plus 1.
To B minus A plus 1. So 3n plus 1.
3 plus 1.
3n plus 1.
3n plus 1.
Because if it's... No, I mean... when I equals 0 and you have the 1, you can just do the B minus 1 plus A, right?
Oh, okay. Sorry, I forgot about that rule. So it would be 3 to the n plus 1. And that would be the solution, correct? All right, cool. All right, so we have that. Yay. And then, what's the second part of the problem? Okay, drive its closed form. There it is. Give the order of the algorithm using big theta notation. Prove the big theta as a result of the expression that you derived. Okay, so we need to find an upper bound, and we can have anything, but it would be, so if we're doing an upper bound of it, so let's say for instance we have O, we want to find O of something. So your big O notation, I would predict, would be 3 to n to the n? Or, no, wait. Well, this is not equal to anything. So, we need to do that. 3 to the n. It's got to be squared to something. N to the n. doing n to the n, that's what I'm predicting my big O to be. Then we would have 3n plus 1. Where is it? Less than. Less than. Okay. 3n plus 1 less than or equal to. We have to make new. Sorry. Three to the n plus 1. We have to make some kind of n to the n. And we could do just 4 to the n. Maybe that will work. 4 to the n. And now I have to do logs, which would be, no, I could still do 3 to the n. Because it would be, come on, I'm going to do that. Because then we can take log base 3 of n on both sides, correct? Because, no, yeah. Yeah, it would be, because 3 to the n, you can make log base 3 of n. Am I doing that right? It's like, no, it's not right. You're horrible. No, that's not it. Okay. Appreciate you guys.
I'm trying to do my own figuring out stuff. I'm not trying to.
Hmm?
I'm just doing my own figuring out stuff. I'm not trying to do
Yeah.
any. Yeah. So I don't know what. Okay.
I'm just trying to figure out like what this would be, because this would probably very well be an exam problem. I could totally see this happening. Hold on, let me look this up real quick. This one is on base B. Base B. No, that's not what I want. That's absolutely not what I want. This is horrible. This is not what I want at all. Okay. Can it be O to the n of n? I don't think that can be right. Well, here's the thing. What would, because we're trying to find an upper bound and a lower bound for this equation. Because we're trying to find the big theta. So big theta is something. And my prediction is that our big theta would be something. And you're right, because if we're doing 3 to the n, it would be, no, it wouldn't be log n. That makes no sense. Or does it? If we're doing theta, we want to have an upper bound and a lower bound. And the upper bound and the lower bound, how about this, right? If we wanted to do like the CS1 way to find out this equation, 3n plus 1, right? We would have to, oh, snap, wait, no, hold on. N plus 1 is less than or equal to nn plus 3n. 3n plus 1 is less than 4nn. n is greater than or equal to 1. Okay. You win, Johnny. Okay, so 3n. Here, let me take you out of the presentation. Stop presenting. 3n plus 1 greater than n. 3n plus n. No, wait, what did you just do? Crap. That's good? Okay. So if we have 3n plus nn, it's going to be 3. No, it's 4n. Yeah, let me see it again. N plus 3 and 4nn. Yeah, you're right. 4nn is less than or equal to 3n plus 1. Okay, and that is for n is greater than or equal to 1 because you can do, no, because it's, okay, so it's 3n up here, right? If you subtract that, 3n, you're looking at me weird, for n is greater than or equal to 1. See, that doesn't seem right either, because look, if you do it,
Why are you subtracting?
Hmm?
Why are you subtracting the statement itself? If n is 1, then you have 3 plus 1 is 4 is greater than or equal to 4. So that statement holds true. So then your c is 4, your g of n is n raised to the n, and your n naught is 1.
so you, like, okay, so for example, let's say for instance so you put 1, that's 1, 1, that's 4, you're right. Okay, so n is less than or equal to 1. Okay. See, like every time that I do this, I try to make it more accurate, right? And I think what's going on is that it doesn't necessarily need to be accurate, right?
Yeah, I think you're making it convoluted.
Too complicated.
So just keep it simple.
Okay.
I think you'll be good.
All right. Okay. So then that's going to be our omega, right? So our omega is n to the n, right? That was 3 to the n plus n to the n, 4n to the n. Oh, okay. So we do, if we're doing 3 to the n plus n to the n, we can also say 3 to the n plus 1n to the n. So that becomes, if we're doing, 3n to the n. Wrote that wrong. Actually, yeah, that actually does make a little bit of sense. So wait, how do you n? I meant 3n to the n. Wrote it wrong, sorry. Okay. So yeah, it would be 3 to the n plus n to the n. So it comes out to 3n to the n. Yeah. Because we're doing, yeah, 3n to the n. And we know that 3n to the n is still greater than or equal to 3, and I wrote this wrong too, 3 to the n plus 1. Yeah. Okay. And then basically you just find any value that for n that holds true, and then you're done. And it could be like, I think like when I was on the Facebook chat, I think the guy was trying to say, it was like, well, make sure that it's like, you know, a single digit number. And I was like, okay, that makes sense. We can do that. That's not too bad. And then that's your big O, right? And we can do the same thing for big theta or omega, right? So something like this, if we have a bigger O to n to the n, our big omega would probably be omega to some value. Like what would we want to put that as? Like, could we do, let's see, 3,1 is greater than or equal to 3 to the n. Oh, so it would be 3 to the n. So we can do 3n plus 1. Did you not? Wait. Yeah, okay. Yeah. All right, I see what you're doing. 3n to the n. So our n to the n is some value. Okay, and that's our lower bound. And then what you would do is then we would just find any value. We'd be like, so for n, let's say if we do n equals 1, then we put 1, 1, 1, and then we find out that this one is actually indeed bigger than this one, right? Okay, so then we can find that our c is equal to 3, our omega is equal to n to the n, and then our n equals 1. And so that's how we can, like, you know, realize our theta, because we have our upper bound and the lower bound. Okay, cool. I think I got that. Next question. Okay. Empirical runtime analysis. Be familiar with the process for empirical runtime analysis and know how it works. With respect to formal big whatever definitions, we are solving constant and showing that we do actually converge towards some constant. Why can't that constant be 0? What is the implication that we converge to 0? Also, some common pitfalls of empirical runtime analysis that we discussed in class. I think that we did pretty well. Like with that, I showed you all the pitfalls all at the same time. It's great. Hold on one second. Let me just move this over here, please. The problem with having a stylus on a board like this, it just never works out the way that I want it to. Okay, so this is the empirical runtime analysis. I think the empirical runtime analysis, like, is he talking about the T of n stuff? You know, where you do, because I remember him doing this in class, right? Where you do this, right? You have pen. Here, let me get off of you, Johnny. All right, you have a pen. Like, it's like a T of n equals 3n. No, that's solving with iteration, right? Where you have, like, not 3 squared. You know, this was a CS1 thing, so it was like n squared plus 2, and then you would basically, like, you know, try to solve whatever that T of n was by putting the n in, solving for a constant. Is that what it's called? Yeah, it was a CS1 thing where you would go through and make T of n like equal. It was like you'd find out that, like, you know, there was a pattern, and then you'd solve for that pattern, and then, like, you know, that was your value, right? Solving for a constant, seeing to what f of n converges to. Okay, so Ravi, can you give us an example? Is there a specific question that I could look at? Let's find out. And did we already do it? Because I think that's pretty much, yeah, his empirical runtime analysis on AVL trees. Okay. Oh, I see what's going on. All right. I know what's happening. So basically, okay, number 7. Let's see what's going on in number 7. Suppose we have some function foo running at time n squared for n equals 4,500. We find that the actual runtime is 0.086 seconds. How long would you expect the same function to take with n with input of 9,000? All right, so that one is, okay, so we have n equals 4,500, and then we have n equals 9,000, and then we have our ON, it's n squared, and then how long will we, or I'm sorry, and then the time is 0.86. .86 seconds. And we have to find out what time should we expect this to happen. Because basically so conceptually, for every n values that we put into it, right, we're going to get an n squared amount of operations back. So if this took 0.86 seconds, then that means that it would have to go through n squared operations to do, so 4,500 squared. This one is the T of n thing, where it was like T of n equals C. Now I have to find it. There's a formula for it, and I forgot what it was. Because you can prove it in, this is a CS1 topic, and I should know better. Runtime analysis.txt, empirical runtime analysis.java, runtime chart.pdf. So we assume a runtime, and we use empirical runtime to prove our assumption is correct. There we go. Thank you, robot 11111. C of n, C times G of n. T of n equals C times G of n. Times G of n. Where, if I'm not mistaken, our T of n is our time, correct? Yeah. Okay. So if we put that in there, we have our 0.86 equals C, which is some constant that we're going to add into this equation, and our G of n is our function, right? So that's our ON. So that comes out to n squared. No, that doesn't make any sense. No, G of n equals n. No. Yeah, you're right. Okay, I'm sorry. So our G of n is n squared, and since we already know what n is, we can solve for C. So we bring that over to this side. It would be 4,500 squared over 4,500 squared. So whatever that is our C. And then what we can do is we can bring this over here. So our T of n, we're trying to find our T of n. And we already have our C, so whatever our C is. And then our G of n is still n squared. But this time our n squared is 9,000 squared times C equals T of n, which is what we're trying to find. Right? Correct me if I'm wrong. Everyone following? Yes, G of n. Okay. Cool. And then our C is 0.86 over 4,500 squared times 9,000 squared. So that is a big number. 0.86 and 48, that's 2. 2. I keep the square, that's 4. Let me know if I'm making any arithmetic errors. Okay, good. 4. I can't do that in my head. My girlfriend's texting me. 344. 8 times 4. 2. No, I'm sorry. That's wrong. Okay. No, wait, that's right. That was right. I'm sorry. That's 2, 3. No, 3, 2. 4, 6, 6, 6.44, 6.64. Someone check me on that. Equals our T of n.
Where did the 32 come from?
Oh no, I was doing I probably did that wrong. Hold on. 0.86. Watch it. Watch this be super wrong. Ah. Oh yeah, that's right. Oh, I'm sorry. Yeah, that's right. Three point 3.44 seconds. Thank you. All right, so that's good. 3.44 seconds. Okay, that one's actually probably going to be one of the easiest things, if I'm going to be honest. So, moving on. Algorithms and design, being clever. Be prepared to examine an inefficient solution to a problem, comment on its runtime, and modify it to improve that runtime, possibly utilizing one of the many data structures we've discussed this semester. That will require you to know about the runtimes of the operations associated with these data structures. So I could ask you to write a method that improves upon the spatial complexity of a given solution. Ah, okay. This one is interesting because I'm not entirely sure how you ask the question. He could do something like, let's say, is everybody familiar, like just generally, like, you know, your runtime for like AVL trees or binary search trees or hash tables, hash stuff? Like offhand? Okay, so we have average, and then we have worst. Okay, so with the AVL trees, the way that we look at it, we have an always like arranging, you know, search function, or I'm sorry, an insert function that will be like, you know, it will be as level as possible, right? So as to minimize, like, you know, the worst case scenario, right? And so for this, it would be order H, whatever that H is, right? And so if it's order H and you search through, it comes out to be, let's say for instance you go with this one, right? And you're like, okay, well I want to do the minimalist value or something like that, right? So we're going with order. The average search time is order H, which becomes a function of I know it's log n. That's what it is. I forgot how to explain it, but there's a way that he did it in class. And we call the thing with big theta, right? Where so you have order H, and with that order, when you're inserting, it's always going to go down H levels. So it's not defined by n, which is the number of nodes that you have. It's actually defined by H, which for an AVL tree, it's always going to be yeah, it's always going to be log n. I just know that by heart. I don't remember how to do it, but that's the same thing with BST. I think like you go for average best case. Let's see. By heart is not good enough. You're right. By heart is not good enough. So let's find out. There's a way to do it. Okay. So we have a minimum height, right? Like this one is going to be height 0. And if we keep on going down, right? If we like conceptualize n nodes all the way down and try to have the longest length possible, right? That's going to be sorry, it's all good. It's going to be I remember, like, okay, so in class he was discussing like what's the minimum height of any tree, and it would be of any n trees, the minimum height would always be order h, which that would mean that if you have an infinite, like if you have an n amount of things in your bag, and man, it's really hard to explain. This bothers me so much. Okay. So you have n things. And you keep on going down the list. I believe in your heart. There was, it's always order h, so the minimum amount that it would have would be n nodes, no, 2 to the n minus 1, right? Because if we had this, and we had 1, 2, 3, 4, okay, so we have this many nodes, right? 4, 2, 6, 7, right? And we have a height of, this is a height of 2. Darn, that's wrong. This is different. Min height is the floor of log n. Okay. Yeah, but I'm trying to figure out how to do it by not actually knowing why that's the case. Because if you, this, like, you know, because the height is defined at 0 at this point, and it's defined at 2 at this point. And if you're doing 2 to the n minus 1 is how many distinct BSTs can you make with n nodes? Thank you, Robbie. Okay, so that's not it. So if we have min height is the floor of log n. Okay, 1, 1, 1, 1, 1. Why is min height the floor of log n? I know you're right, but how do you explain that? Like, because we have this, right? And we can, I can see the pattern. So you have 4 here, 2 here, 1 here. So it's always 2 to the n. We can't do 2 to the n because if we do 2 to the n, 2 times 2 is 4. Maybe it's plus 1 to the n plus 1. That'll be 2 to the 3. He provided the induction of that height with an AVL tree of n nodes that will always be log of n. He proved with induction. Oh, okay. I see what he did, right? We just need to know it by heart. Okay, fine. I thought we didn't have to know it by heart. Johnny, you lied to me. You said by heart is not good enough. Okay. I said is good enough. Oh, okay, you said is good enough. I'm sorry. I read it wrong. All right, so let's go back to what I was doing. Best case scenario for an AVL tree is log n, right? I'm pretty sure. And I think that the worst case scenario is n log n. Or is it log n? I know that a BST, the best case scenario is also log n. And the worst case scenario is n log n. No, because it would have to traverse through everything, right? So you have, let's say, for instance, it took, like you have, no, the BST, because it's not balanced, right? It would be the worst runtime would be n, and this is for insertion, by the way. The worst case scenario would be n because it would devolve into a linked list, right? An AVL tree, by definition, because it's always, yeah, thank you, Ravi, because it's always like, you know, it's trying to balance itself at every turn. It will never fully devolve into a linked list unless you really just write your AVL tree poorly, or it's not actually an AVL tree. So the worst case would be n log n for an AVL tree, because let's say, for instance, you have an infinitely balancing, you know, tree. No, insertion would always be log n. Because even if you went down, like, you know, the biggest path you could possibly take, it's always going to be balanced. It's always going to be order h, which in turn is order 2 to the n minus 1. Because that's order, okay, so yeah, 2 to the n, yeah, that's right, 2 to the n minus 1. That's what makes sense. And then the hash table, which is my favorite thing, is order 1, worst case scenario is order n. And the reason why the hash table is, I'm pretty sure best case for BST is order 1. If best case is, are you, let's find out. There it is. Best case for BST is order 1. Let's see. Binary search tree. No, always log n. The worst case scenario is order n, so I did get that wrong. So, and if you're going with time complexity, nope, still the same thing. No, the reason why its best case is always log n is because you have to traverse down n trees. I'm sorry, you have to traverse down h trees in order to get to your node, right? Because if this was your node and you're looking for the insertion, bam, you're done. That's order 1. But the minute that you put something in like that on here, that's order 2, and it's technically order n nodes. And then once you start putting, you know, more down, you start seeing it diverging into order log n, because in reality, the best case insertion is always order h. And order h is the height, which is 2 to the n minus 1. Dot, dot, dot. Best case order 1, if the BST is devolved into a right-leaning linked nest, then inserting, deleting, or search something to the left of the root will be order 1 operation, and vice versa. That's from his notes. Please show me these notes. For insertion, are you sure? Which, that's from his notes, September 7th. Example, the root is 2, 3, 4, 5, 6. Then we insert 1 to the tree. That is order 1. What about 7? This is for best case. Okay. That makes, okay. Yeah. No. You're right. So best case scenario is technically order 1. You're right, because I was looking at average. I apologize. 7 will introduce worst case. Yeah. Okay. You're right. So best case is technically order 1. You're right. I'm sorry, guys. And then, so let's move on to hash tables. Hash tables, best or average case is order 1, because we expect order 1 with a hash table, and then worst case is order n. Right? Okay. Best case, order 1. Because we can introduce, like, you know, something like that. Okay. And the worst case is order n. Okay. And then what else did the question ask? We will inquire how the runtime's operations associated with these data structures are also working to write a method that improves upon space complexity, i.e. memory usage. Okay. So, this I feel like has a direct relationship with the Sneaky Queens and Sneaky Knights programs. And one thing that I learned from those programs is to kind of think outside the box. Because when you start, like when you do Sneaky Queens, like the first thing that you like attempt to do, or at least in my experience, was to do something that was order n squared, right? Because you conceptually think, okay, I have to match every queen with every other queen, so minimum I have to look through the list twice. That's already n squared, and you needed to have it n plus n, and then for knights you had to have it on. So you're kind of like, man, what do I do? And one of the things that I thought of was like, how do I look at multiple values all at once? You know, does it, like, you know, I don't want to talk too deep about Sneaky Queens and Sneaky Knights because one, Knights is not out yet. We haven't, like, it's not, the due date's not out yet. So I might, like, you know, divulge too much information, but I do believe that this number 4 is asking about, like, you know, specific things. Like it's asking about, like, you know, you're given a block of code, and in that block of code you're saying, how do we make this better, right? So if we have, like, you know, a for loop, and it's doing something, you know, it's counting a variable more than once, right? You have to identify that and then try to emit that variable that it's doing. So that one's actually going to be tricky. Does anybody have, like, an example from this? Because we can look here. Write an efficient function that takes in its input as a sorted array of n elements and returns true if there are any duplicate values in the array. Otherwise, return false. Give the big O runtime and spatial complexities for your solution. The function signature is n duplicates. Okay, that's actually a pretty good talking point. So takes it. Function that takes its input as a sorted array. Okay, so what goes in is a sorted array. Function. And the output is a Boolean value. True if there are any duplicates in the array, otherwise return false. Boolean value. True equals duplicates. False equals no duplicates. Okay. So if we're doing a sorted array, we have the sorted array, and we want to put some function that returns true for duplicates and false for no. Obviously, the easiest solution is to just run through all of them, and then that'll be order n. So you could write, like, you know, a for loop that would just go through the entire sorted array and say, hey, like, you know, if there's any duplicates, then go ahead and point true, and go ahead and point false if there is none. There is a better way to do this, obviously. Does anybody have any ideas? Because if I do hash if collision return true. See, the thing is that that would be a best case scenario of order 1 or order whatever value that you get, because you still have to insert all the values in, like, you know, from the sorted array. Like, you know, your function would be insert into hash set. Let's make it simple. And an insert into the hash set would be best case scenario order 1. And then, well, actually, no, that would actually be an insert into order 1, but it's all dependent on this n, right? So if you're running through the entire sorted array, you have to put a for loop in there anyway. So this would just be order n still. You understand what I'm saying? So I feel like because we already have the sorted array, and it's sorted, so that's great. I feel like that's not necessarily a clue, but let's say, for instance, we have 1, 2, 3, 4, 5, and then we have 1, 2, 3, 3, 5. Okay, so if any for loop, it actually goes through each one, right, and then goes down the list, and then if it finds something, then that yields true. So for the one that you proposed, it was insert into hash set. So we have the sorted array. We have array I. What was it? No, I'm sorry. So it's like let's call our hash set hash conclusion. Okay. Hey, Andrew.
Hello.
So we actually have an interesting question. How do we make this as efficient as possible? We have a sorted array, and there's a function that we manipulate it to return a Boolean value if there are duplicates. The most efficient way to do that.
So it just takes in integers?
Yes. Wait, let me just double check. Actually, takes in integers.
Wait, so it takes in one array and then takes in another array and then has to return Boolean?
No, it just takes in one array. So our function header is Boolean duplicates.
Oh, I get it now. So like the second one would return true.
Yeah, it like basically do the return true or false, and then you have an array.
Yeah, just put them all into a hash, and then if there's create 2 hash sets. One would be like your main hash set, and then your second hash set will be like a check one. So you go through firstly you just insert it just as it comes, and then if there is already something in your hash set, like if it's already true, so to speak, on that spot. Wait, and that's all you need. You only need one hash set.
Yeah. So here's what I'm thinking. So you have this array that's already, and it's sorted already. Okay.
Right.
And so in order to put it into the hash set, what you would have to do is you'd have to put it into a for loop, unless there's something that I'm missing, right? So you have to do like, huh?
That's right.
Right. So you have for int equals, no, sorry, not int. And let's do I equals 0. I is less than or equal to array dot size, or is it length? It's length.
Yeah, it's length.
Length I plus plus. Right?
Yep.
I have a cold and stuffy nose. I understand. It's okay. Would you like some tea? No need for a hash set. Can you do array j equals j plus plus return true.
So are we guaranteed a sorted array? Because if it is, then you can just do that.
Yeah, you're
If
guaranteed a
the
sorted
next
array.
one over is the same as your current one, then it's
Mhm.
obviously a repeat.
That is very clever. Ravi wins. Because I was about to say this, like your hash set, it makes sense if you want to do the hash set, but the problem is that you're putting it into a for loop, which is already order n, right? If you're doing, yeah, exactly. So Ravi's
I think my
Ravi's
way is still order n, because you only go through the for loop once.
exactly, but like
It's
this
just
is
more conditional statements is all.
yeah. If we want to make it as efficient as possible, what we want to do is, let's see. Oh no, wait, hold on. So we have array.
Yeah, no, you don't have to rewrite it. If you go up and just put that what Ravi wrote into your for loop, then you're done. Right here.
Is it it's still order n though, right?
Yeah.
Is there
Can
any
you
way
make
that can make it better though?
No, because you have to go through the whole thing. What if there's a 1 at the end of... Oh, wait. Yeah, because you have to go to the end. Because think about it. What if it was 1, 2, 3, 4, 5, 6, and then on to infinity, and then like it repeats once at 1,000, you know? You have to go through the whole thing to check if there's a repeat till the end.
It seems too easy.
There's no way to check if there's repeats without actually looking at all of them, isn't it?
Not necessarily.
Do this then. See how it's size 5?
Yeah, this one is size 5 technically. I just made it. Right.
Oh, okay, never mind. My idea wouldn't work. I was like, if the last element isn't equal to the array size, then I would say there's a repeat. But then I remember that there could be a disconnect, you know? Like it could be 1, 2, 4, 6, 7.
That is true. You could do that. But think about it this way, right? So if we have, because I like the idea, is if we have 1, 2, 3, 4, 5, and we know it's size 5, right? If that is the case, then we know that no, that's not right. I can't do that either because it could be 2, 4, 6, 8. We just know that the array is sorted. We don't know that the value starts at 1, and we know it's an int. So it could be
I
any
think
value.
order n is as good as it's gonna get.
Binary search. Binary search would be log n. Yeah, because if you do, no, if you're doing an insert, but no, still
You'd have to do binary search.
you have
just
to. Yeah, if you make it a binary search, it's still going to be order n.
Yeah, it's gonna be n log n then.
Yeah, it's going to be n log n because you're still doing the for loop. See, that's the problem. Like you can't get out of the for loop, but it's already in an array. I feel like if you have it in an array, then there's something that you can do to it. You're not searching for anything. That is true, but inserting it into a binary search, it's order 1 each time, and you're doing the for loop through the array. So it'd still be order n. I don't think you can beat ON.
Yeah, you really can't. Order n's not that bad, honestly.
No, I'm not. It's not. No, it's not terrible, obviously, but
like the definition of efficient, order n is pretty efficient.
Let's see if there's something.
Yeah, like on a test, I wouldn't mind if I get a order n for something that calls her efficient.
Yeah.
Are there answers to any of these or no?
No, there's never answers.
Good old John.
This one's really hard. If you dredge up synology CS1, write an efficient function that takes a sorted array of n integers and returns the number of times key appears in the array. The function signature is, okay, key count. Takes a sorted array. Okay, so we know that there's duplicates. So, all right. This one is pretty interesting. I like this one.
Isn't that also order n?
Not necessarily.
No, it's usually the exact, well, not exact same thing. You just literally go through the whole array and increment key by 1 or count by 1. Like if array of I is equal key count plus plus, and then at the end just return count. I don't get it. Is it supposed to be better than order n?
I feel like there's always something better than order n. You know, like I feel like if it isn't better than order n, then like because I don't want there to be a question, right? Where it's like you have to make sure it's better than log n, and you're like, oh, but I figured out order n. That sounds great. And then you're kind of stuck because you have to figure out a way. Like, if we have a size, right? So we have the number of keys.
No, the key is what you're looking for.
Yeah, the key is what you're looking for, the number of keys, because that's what you're returning.
Right.
And you have to write a function that takes the sorted array of n integers and returns the number of times key appears in the array. So whatever key is, so if it's already sorted, right? You can actually, so like take for example, let's say for instance you have all the numbers from 1 to 100. Okay.
In consecutive order.
In consecutive order, because it has to be sorted, right? And your key is 35. You take the size, still O(n) if the last element equals key. Not as okay. You take the element, okay, and you take whatever key that is, right, and you go to the have count that increments every time binary search returns true.
You don't have duplicates in binary search.
That is true. Well, no, because you have to go through the entire thing.
Yeah, you still have to create your binary search tree, which is log n, and then you can do your thing. So it's already not.
Yeah. So like it has to be inside the array as you do it, right? So
Yeah.
what I'm thinking, right, is let's say take for example, right, 1 to 100, right? Your key is 35, right? You go to the middle
Mm-hmm.
of that search, right? If your key is less than, the middle, then you already know that it's not there, like it's not in the top half, and then you divide by half again, and then you divide by half again until you get to 35, and then once you get to 35, then you can see how many times you have 35 above it or below it, depending on how you write the function. You understand what I'm saying?
That's assuming that you have 1 through 100 elements in consecutive order, though.
You have 1 through n elements sorted. So you can take the size of that array.
Let's just work with the smaller. So if you have that and the key is 8, I don't understand what you're saying. So you go to 5 first.
Yeah, and you find out whether
you go to array size over 2, basically, right? Half of it.
Yeah.
And then you would see if it's greater or lesser than the key.
Yeah.
And then you would check the upper half because 5 is less than 8.
Mm-hmm.
And then you would keep doing that until you find your thing.
Until you find your 8.
Okay.
And then once you have that, then you're like, oh, I already have my 8. Let's check above and below using a recursive function, right?
I get what you're saying, but what if it's like something like that?
Okay, so 1, 2, 3, 4, 5, 5, 5, 5, 5. All right, and then you have a bunch of 8s, and you're looking for 8.
So you go to halfway point, which is 8, and you found it. Then you only search the top half, and you lose all the bottom half 8.
No, because you're doing a recursive function up and down. And once it returns not 8, then it returns the recursive function. And then then it goes up all the way. So you always have your n is n over 2. Your O(n) is n over 2.
Oh wait, hi guys. Can I talk?
Yeah, definitely.
Okay. This is Jasper. Hi. So just real quick, what I did in this part is I put my base case is the array length at half equal to the number we want. If it is, go up and down until you find or keep going up and down until you don't find your number and just keep incrementing. If that makes sense.
Yeah. Okay, so wait a minute. Jasper, wait, are you tagging along with somebody? Hold on.
Well, whatever.
111. No, you're not 111.
What?
No, never mind. It's all good. All right, so explain to me one more time.
So instead of splitting the array and accidentally removing some of your values that you might have accidentally had in your array, your base case in your recursive function is, first of all, is the number at that half length what we're looking for? If it is, immediately return that value. Immediately return 1 plus every value that's the same as that value until it's no longer that value above and below it.
I get it.
If value equals key,
Yeah.
then return the same function. Return.
Well, I just did while a minus minus is equal to key, add to total, subtract from a, where a is the length divided by 2, and then do the same thing except it's plus plus.
Okay. That actually makes a lot of sense. So the runtime would be, in that case, since you're doing that, you go into the middle of the array, right? Is that where you start? No.
Well, it's recursive, so it's log of n, but you multiply by k, where k is the amount of times that you have key in the function.
Okay. Wait, log of n times k?
No, sorry.
Plus k, right?
Plus k, yeah.
Plus k.
Which is actually just order log of n, right?
True.
Yeah.
All right. Yeah, that actually works out a lot better. So now you have log of n. So
It depends, unless the whole array is the key.
if the whole array is the key, that is the worst case, and then that would be order n. But your average case, because we're going to assume that it is not, the worst case scenario, because we're optimistic, it would be log of n.
I thought he said you're always supposed to return the worst case.
Fine. I want to be optimistic, guys. I think that's probably the best solution.
So like when you write this as a solution, I wouldn't discount the k. I would leave the k in as the solution and then write a note saying where k is equal to whatever.
Where k is equal to the number of
because that is pretty significant, I think.
Yeah, that's true. Because if k is equal to n, then it would be order n plus n. Or order
So
log
it would
n.
change from log n to a n,
Yeah, no, you're right. That's true. Okay. Then what about last one? Given a sorted array of integers, determine whether any two elements add up to some particular target integer. The function signature is has target sum. Oh God, went on the internet. And internet array or int array int target.
Didn't we already do this?
No, this is number 3.
I meant, sorry, in class.
Oh, did we? I might have not have been there. I'm gonna be honest.
I think we did.
Oh, did we? Okay, then I won't go over it.
Well, it's still nice to go over. I can't throw it off from the top of my head. So.
Yeah, I can't. Well, I definitely can't because I probably wasn't there. But or I completely forgot. Professor, if you're watching this, I was totally there at class. Okay. Given the sort of yeah, I remember this. I remember that he did it, but I don't remember how he did it.
I think he did this in CS1.
Did he?
Maybe not. It's been a while.
Doesn't he post out his notes? Where's his notes? He doesn't print out his notes anymore? Because it was there.
He has them. Just have to find it.
Yeah. No, because he has the big data and then he has the runtime chart. Oh, wait, I'm sorry. I'm in the wrong thing. It is after generics. No, I'm sorry.
August,
It
August
is
24th, next to notes. Right there.
where?
That code block. That big code block right there in
Oh,
your face.
oh, okay. So what he does, if sum is too small, array I is bringing us down increment I. If sum is too large, array J is causing major decrement J. Otherwise, we found our target. Huh.
Oh, he's just moving in from both sides of the array till he finds it, right?
Yeah. That is... Okay, so yeah, the brute force is n squared, and then he has one that's n log n, and then he has something a little bit more articulate that's on. And that's probably the best thing that you can do with that. Well, the best thing that he will try to do.
Did he hint during class or any lecture what the coding part of it might be?
I have no idea, because if I'm going to be honest, CS1 I did with Guha, but discrete I did with Szymanski. So I'm like really worried about this test because I honestly have no idea.
Because usually his number one, number one for the test is going to be like 20 points. It's going to be literally coding out something, syntax and all.
Yeah.
So that's going to be the biggest part, and then the rest is just like you get given stuff. Like number one is the one where you have to be creative, and usually he hints during the lectures what he might be asking, but I've skipped too many lectures this semester, so.
Oh man, you're not getting any bonus points then.
I could think of what he might say.
I mean, the whole coding up thing, like I'm worried that he's gonna do something like take up like this, because I remember Guha, his tests were insanely hard, but like he graded on a curve, so it wasn't terrible.
Sometimes he curves too.
Does he really?
Yeah.
Oh.
In CS1, one time I got like a 69%, and that was a B+. So.
Oh, okay. Yeah, he doesn't curve as much as I would like in discrete.
Depends how everyone does and how he's feeling, I guess.
Yeah. So, I honestly have no idea what the question would be. I was actually thinking that he was going to do something from the first few lectures where he's just like, oh, solve this, like, order notation, da 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 da. Or no, I'm sorry, solve this order notation. That makes no sense. Like, derive this sum, and then, make sure you present it in its closed form. Then find the runtime analysis, and then that's how you should get the, this thing. And I'm like, oh, okay. Well, that's like a whole thing that I have to figure out. But the coding part of it, as long as he doesn't do the thing where you're given part of the code, you know what I mean?
The header?
No, not the header. Like you're given so I remember specifically like Guha did this with like stacks or queues, right? Where he's just like, this is a stack, but some of the things are missing. Go ahead and fill them out for me. And it's like, and like A is like an integer value or a variable. B is like, a little code block of a for loop. And you have to place it in different spots.
No, he doesn't do that. From CS1 at least, it's like, it'll be like, write an efficient code that takes in an array of strings, something blah, blah, blah. And then he'll say what you're being passed in, like string would be like blue, blue, green, blue. And then all he gives you is the header.
Oh, really? So you have free domain as to like what you should write.
Yeah, it even says like you can create like auxiliary functions if you want and shit like that.
Okay. Yeah, I mean, all right.
But there's only so much you can do with pencil and eraser. You're just constantly changing around because you run out of space.
Yeah. And what was I going to say? It was the one thing that I'm not a big fan of is like, well, like he could write something like, would he say that it has to be in a certain time? Do you think? Like it'd be like, make sure that it's in ON time since it's CS2.
He's never done that, but it should be obvious what it should be. Because like in CS1, when we had to write up a code for some data structure, we already know what the runtime of that data structure is, you know?
Mm-hmm.
So then he'll like make you write that code out, and at the bottom it's like, what is the runtime of your solution?
Mm. So let's say Johnny said something real quick. I think based off the notes, we give a function and we improve it, which easily can be combined with the whole theta and summation stuff. Is that the situation with everyone here? Andrew, what do you think?
Nah, the number one, he's not going to give you anything. He's going to give you the input line and then the header.
Oh yeah.
He does that every time.
Okay. So real quick, there's one thing that I did that Johnny wanted to go over. What did you say you wanted to go over again? I forgot what it was. No, maybe it was you, Andrew. I don't remember.
The 2-4 tree.
The 2-4 tree. Okay. Let's figure that out. Because if you're saying, I'm going off of your word, Andrew, that like it's like a big, huge 20-point question, and then it's like a bunch of little questions after that big 20-point question. And I've seen that on the first discrete exam.
I took it for discrete too, but it's a little different from the CS portions.
Okay. And, you know.
Because for discrete, like all of them are kind of big. You know, they're all like 20 points.
Yeah. Discrete is just you will die. That's what's gonna
last time I took CS1, he had like one page, just 30 points full of runtimes. He's like, what's the runtime of this? What's the average of this? What's the worst of this? What's the this?
That's crazy.
Yeah, I got like 10 points on that.
You're saying 2-4 trees. What did you need on 2-4 trees?
Like deletion?
Okay. So.
Because I remember that being a little tricky. Go over that.
Do I still have a 2-4? Is there a 2-4 tree on here? No. Could it be a red-black tree? I don't know what a red-black tree is. But what specifically about the deletion that you? Oh yeah, because we have to traverse through it. Oh dear. Okay. Yeah, he said specifically that we have to like traverse through a 2-4 tree, or know how it works when you add and delete it and whatnot. So with a 2-4 tree, you have, let's say you have a value, right? Whatever this value is, and you have 2 spots per, and then you have up to 4 children.
Right.
Okay. And then when you, what ends up happening is when you insert, hold on, let me go ahead and look at the lecture real quick. Because the only lecture that I know that I messed with was Bloom filters, which that would be my question.
Bloom filters aren't too bad though.
It's basically a hash table, right? It's like
just like multiple hash tables.
Okay. That's what I want. Okay. Preview. Okay. Okay, so insert 10. So we have 10. Then you insert 40. 40 is in there. So it keeps on going until it gets to 4.
Yeah, and then it has to blow up.
Yeah, so it has to blow up, and for the class, right? This is not necessarily in general, but for the class, you want to do the let's agree always squish up the third element. So that's going to be 40. So 40 goes up, and now 40 has 2 children. Because in a 2-4 tree, it always has to have 2 children, correct?
Yeah.
Okay. And so if we continue inserting, it goes down and it goes to 32. And then we have insert 1980. Oh, wow. I forgot that. That's insert 1984, insert 126, insert 86. And then once 86 comes in, now we have 4 here. We can't have that. So Okay, this is my prediction. What we'll do is we have to do 180, and 180 will squish up
Into the 40, right?
Yes. But let's see if that causes any errors. So if it squishes up into the 180, then that means that we have 180 here, and then we have the 40 here.
I think it's just going to be 40, comma 180.
Yeah, it's going to be 40, 180, which is valid. That's fine.
Okay.
But then we have like 86, 126, and 1984 that we have to deal with, right?
So the, what do you call it? The blank spot left by 180 turns into a line, and it points to 1984 from 180.
Sean de Fontaine. Gee, I wonder who that is. So, okay. So my prediction is that it will, like the blank space left by 180, it's going to cause the split, right? Because that's what happened here.
Yeah.
Right? So you see it. Where is it?
Because it's greater than 40, so it couldn't go into the left side.
Yeah. So it's great. Yeah. Well, let's find out. 180 goes up. It pops into the 40, so it goes onto the right. All right, cool. We got it. Awesome. All right, so now we go in.
See the 86, comma 126? The line is pointing at in between 40 and 180 because those values are in between 40 and 180.
What do you mean?
So, like 40, comma 180 has 3 children, right? Because it can either be less than 40 or in between the two values or greater than 180. Yeah, that's it.
Oh, okay. I see what you mean. And well, so here's the thing, right? It's a 2-4 tree, so anytime that you see well, hold on, let's keep on going. Because I think there's a point in time. So you insert 23. Okay, so I think my question is, okay, let's say for instance you insert something that would make it have 4 children, right?
Right.
Pretty sure he did this in class.
So right now it will become 4 children, right? Because 25 will go up to the left of 40.
So it will go up, and then now we have 4 children. So, okay, so...
But there's nothing wrong with this. This is stable still.
Okay.
Until one more gets thrown into the head.
Until one more gets thrown into the head. And so what happens is that if one more gets thrown into the head, right, is that it will go up.
Would it drag stuff up with it? I don't know. I forgot.
Well, let's find out. 125, 40.
Wait, can you not insert into the head?
No, you have to go like all the way down.
Okay, so bottom up.
Yeah, it's bottom up.
Okay.
Unless there's... Yeah, no, it's bottom up and then it squishes up. So let's say, for instance, instead of this being a 46... No, let's say that 46 is there. But let's say you insert another value that would go into that node, that particular node right there. It would have to scrunch up, and then in turn of that scrunching up, then it would create another node. It would create another parent.
That's why inserts always order log of n because of height. So.
So we're looking, wait, let's see. 86 gets squished up because it's always the third one that gets squished up. Now
There's many children.
Okay, so now the root node has an overflow. And so, okay, so what happens is that 86 has to get squished up again, right? So if 86 gets squished up, then we have 25 and 40, and then 180 on one side. Right?
Yeah.
Okay.
But what happens to 126? Oh, it just sticks to 180. Makes sense.
Yeah, so essentially, okay, so if you see the difference between these two, okay, so 86 gets squished up, 25 and 40 go to the left, 80 goes to the right. Now we have between 25 and 40, right? We have 32 because that does make sense, right? And then you have
Mhm.
41 and 46 on the side, and you have 126 that's connected to 180.
Now it's stable, right?
Yeah. Oh no, wait, but now the root node has an overflow. Wait, what?
No, I
Where?
think that's just from the previous slide. He
Oh,
just hasn't deleted it.
This previous slide. Okay. So yeah, now this is stable because we don't so the rules of the 2-4 tree, right? If we go back up, I think he has the rules. Unless he doesn't. No, wait.
Nope.
Oh, it's on the bottom. No.
You passed it.
Did I?
I don't know. You're into deletion now.
There's so many slides. Insertion. Okay. Oh. Okay.
So that's the final. What it's looking like.
I
Yeah,
don't
because
think
everything has less than 4 children, or 4 and 4 what do you call it, elements. So it's fine now.
So yeah, that's fine because it has to be less than 4 elements, and any particular node can only have less than 4 elements.
Yep.
Right.
Insertion's pretty straightforward though. It's just
So the deletion is what you're looking at, right?
yeah, some crazy stuff happens here. Like there's some like AVL rotation type stuff that happens.
All right, so if we delete a non-leaf node, then we get the BST style, replace the largest value left in the subtree, replace the smallest value in the right subtree. So that means that we're going to bring up the value from the leaf node. Okay, so if it's a non-leaf node, if we delete a non-leaf node, we do a BST style. Wait, what? Oh, okay. So if we're doing leaf node deletions are the only interesting deletions. Okay, so we delete 86. Whoa, wait a minute.
That's not a leaf node.
Oh yeah, wait, what?
I don't get it.
That's the root.
Let's just follow it, because I think he wrote it wrong. Because leaf node, if you just delete it, it just deletes. It's gone. It doesn't matter.
Mm-hmm.
So anything that has children, if you delete it, is what messes stuff up.
Oh, look. Okay, so what happens, we don't know which element moves up, so we take we grab an element with multiple elements. So his analogy was you have to take from your cousin or your brother or something. And if we put so we put that up, right?
Yeah. Oh, 23 goes up, 25 goes down.
Yes, because if you do 22 there, it's not between 25 and 40. That's where you get another challenge. So you want to bring the 23 up and then move the 25 down. Hopefully, yes, I got that right. Okay. And then, so now the tree is balanced once again.
Right.
And then if we delete another one, if we
41.
delete 41, okay, so this one we have no siblings that were willing to give anything. So, but it's a leaf node.
No, because if you delete 41 and you move 40 down, you can't take 25 and bring it up.
That is
That's
true.
that's where the problem is right now.
So, okay. So what I think is, so I'm going to imagine that this function works recursively, right? It's probably going to work. Okay. And so we can't borrow from any of the children, and 41 gets deleted. So we can't just bring 40 down, can we? Delete 41.
I think you bring 40 down, but you don't take 25 up. You gotta do something else.
Yeah, because
Just
that
keep
would.
scrolling.
So, well, hold on. Let's try to figure this out before we scroll down. So if we move 25 up and do 40 down, then we have that one. And if we do it again, then we would have craziness, because 10 wouldn't work either. I
don't think the 25 is gonna move at all.
You don't think so?
Fuse and drop.
Fuse and drop. Oh, okay. So fuse and drop. Combine 25 and empty node. Okay, so that one fuses together, and then that's where you get the 2, 4. So yes, this is a crisis. And then we drop the 40. No, yeah.
Drop the 40,
We
right?
have to drop the 40. The 40
No, we
down.
No, we do.
Okay. So for deletion, if we go back up, in situation where we do the leaf nodes, it's fuse and drop, right? Unless there's another one. I'm pretty sure there's another example here as well. Delete 126. Wait, what did he do? Oh, I think that was just okay. Delete 126. So if we delete 126, we can't fuse and drop that because there's not an additional value there.
Okay.
Right? So what we would do fuse, drop, and now that's an empty node. Oh, okay. So if that node is empty, right? It does the thing where it borrows from the it takes the 40. No, I'm sorry. It drops the 46 and then it takes the 40 up. No, that wouldn't work either because there's a 41 there. So
I think 41 gets dragged up with it, just like as if it's following the path. So if like 41, 40, 46 just all rotate 1 clockwise.
okay, yeah, 40 moves up, 46 moves down. Well, then we have 40, 46, and then
Or maybe not.
So, but that's not going to work because you have a 41 in the wrong side.
Yeah.
Oh, Sean DeFontaine left the group chat. So then you delete. Okay, so then you delete 126. Whoa, where did that come from?
That's the initial thing that caused this all.
Oh, okay. So now you have 40, 23, 41. That doesn't work. And we want to. 41 moves over to the left, becoming left child of 46. Oh. Okay, so it borrows the child. 41 gets adopted by 46. Okay. So with that, you have fuse and drop, and then we have the borrowing. So in this case, when you do deletion,
Ta-da!
ta-da! Yeah. when you have okay, so you have deletion, and you delete 126. You go up, and now we have something that doesn't work. So honestly, it's like the simplest solution would just to be like 46 follows 41, right? Did he write this? Like he didn't code this up in class, did he?
And say he tried to, and then it was really bad. So he's like, I'll just know it conceptually.
Okay. Runtime for insert, delete, and search. Okay, so yeah, I remember that. And then that was it. And then you have the proof if you really want to look at that. Okay, so for 2-4 tree deletion, there's a few things that you can do. If it's a non-loop node, then that's how you start out with BST style, right? Oops. There we go. Okay. If we delete a non-leaf node, we do a BST style. So with the BST, like you take out 40, and then you have to move, replace the largest value in the left subtree. That means you always bring up a value from the leaf node. Okay, so it's always that rotate thing, right? And if you have an error with rotation, you do a fuse and drop, or you do an adoption, right? So fuse and drop only happens if you have an empty node and you have no one to like you borrow from, right? So adoption's always first. You know what I mean? Because look,
Yeah.
you have it here, right? You deleted 86, it comes out, and now what you do is you do that rotation, right? So 40 goes up to the top, 46 gets dragged up with it, and then you have, oh wait, no, I did that wrong. 46 goes up, 40 gets pulled, and then 41 stays the same. And no chain leaf node highest node shouldn't to worry about, so we're good there. Okay, so that has no conflicts. If you have a conflict, then you either have the adoption or the fuse and drop. With that, so yeah, so you always do the leftmost, the highest leftmost value or the lowest rightmost value. And for this class, it's always the highest leftmost value, and you pull that up, kind of like how I think one of his analogies was when you're pulling one thing up, everything kind of gets dragged along with it, and then that's kind of what happens.
Yeah,
And
that's the BST style.
yeah, the BST style. So we all know that. And then we have the fuse and drop in certain cases. So if you have this leaf node that's disappearing, then we fuse from like a parent.
No, this one you don't fuse drop yet. I think you just rotate it.
I mean,
23 goes down,
like,
23 goes up.
Okay,
Next one you might have to fuse and drop.
that's right, because you want to.
But you still have enough to lend over from that left side most leaf.
Okay, here we go. Non-leaf, pick highest from left or lowest from right. 2, leaf with sibling rotation. 3, leaf with no sibling, fuse and drop, or adopt case. Thank you, robot. 1111111. Yeah, so that is actually. Do you have any other questions about the 2 first tree deletion?
No, but I'll probably forget it by tomorrow.
Don't forget it. There's probably going to be a question on it. Yeah, that's pretty much it. I mean, it's not terrible. What about Bloom filters? Could you if you could explain to me Bloom filters real quick? That would be fantastic.
Do you know how hash tables work?
Yeah,
You know how it's just a tick mark, right? It's not actual values.
you're storing like keys, if I'm not mistaken. Because I was looking here and he was like, okay, you have a tick mark and you have a hash table.
I thought Bloom filters were Boolean.
I mean, this is the one class that I missed out on.
They're optional Booleans, so you can be whatever you want. But he did Boolean specifically because it's the easiest to conceptualize, yeah, and it's just the fastest way of doing it. You would have to store less memory, space complexity.
Mm.
So keep scrolling down. You'll see like this one right here. So a Bloom filter is just a bunch of hash tables.
Mhm.
So like, so you put let's say you're putting in the word like game into your Bloom filter. So just for the sake of matching up perfectly, you're gonna have 4 hash tables. And for the first letter of game, G, you'll put that into your hash function for your hash table 1, and it'll spit out a certain number, right? Like let's say 8. So then there's a tick mark there.
Okay.
And then for A, for the second letter, you go to the second table and you put it through your hash function, and it puts out 1. So there's a tick mark there, and so forth and so on. So later when you come and search to see if a game is in your Bloom filter or not, you do go through the thing again. If all the tick marks check true, then game is in there.
Okay. So this is multiple hash tables, correct?
Right.
Okay, because I see hash table 1, 2, 3, and 4, and you're inserting.
So he's inserting Rob into every one of these tables.
Yeah.
And those little asterisks are what returns after it's been put through the hash function.
Okay.
So later on, when you're retrieving to see if Rob is in fact in here, you like put it to the hash function again, and if all of these tick marks return, true, then you know that Rob is in it.
See, that's weird. What's the purpose? Like, is this like faster?
The purpose? I'm not sure.
For Bloom filters,
Yeah.
it's just wicked like space saving.
Oh, so this has to do specifically with spatial complexity. You're kind of.
Oh yeah, it's like ridiculous compared to everything else. What you do lose though is the probability that you will get something wrong. So.
So the more that you use this, the more likely it might not actually return anything when in fact you did put that in there.
Yeah, it's like every hash tables, so like 1 through 10, if there were 10 values, it would be like 10 times 13 times 20, and then if you multiply all that together, and then you get like some percentage of like chance that you'll get it wrong, which is fairly ridiculously small, like 0.01 if you do it correctly.
Okay. But there is that chance. There's that one chance that you.
Yeah.
There is a chance.
So maybe an extra credit question. They use this in like biology because the chances that that thing is wrong may be very small, but then they're like, oh, let me check to see if that's true, and then they look at the DNA and they're like, that actually is false. That was a false positive. So then they double check it and they're like, that doesn't actually hold with our findings, but that's how they check all their strings or whatever.
Okay. That makes sense. Bloom filter retrieval. Okay. And then defining using Bloom filters. Okay. Cool. Roy, did you have like a question that you wanted to go over? Is there something that we haven't like overlooked or anything?
It says practice exam problems include code up skip lists. I don't know if you guys went over that earlier, but.
Oh, okay. So the skip list.
Oh man, I forgot all about
skip lists. That's gonna be fun.
Yeah, it says, admittedly, that's a tall order simply to practice up for the exam. But,
I don't think he's going to have us code up any of the data structures.
well, hopefully not.
At least not 2-4 trees, because...
Oh, it says coding this up will be your 4th programming assignment, but I don't know.
Okay. Actually, that's a horrible skip list. But as far as skip lists are concerned, what you do is you have a series of values that are in order. So you have 1, 2, 3, 7, 13, 15, right? And what you have is you have a call. If you have certain heights for each one, right? And then in your certain heights, these are kind of like linked lists, right? Where they point to the next value over. So this is your standard linked list. But if you added a height complexity to your linked list and you only added a height complexity to certain values, let's say for instance you added, for every second value you added an extra height. Oh wait, I added too many values. Get rid of that. And then, yeah, that's it. And this one points to that one. And that one points to this one, right? And the idea for the skip list is it always starts at the top when you're searching. And when you're at the top when searching, let's say for instance you want to search for like 7. So you go over here and you're like, okay, is 1 7? No. Is 3 7? No. We want to go up more. Is 13 7? No, in fact, it's lower. So we go back to 3, and then we go down. And we go down one level, and then we go, okay, let's go to the next one. Is 7 7? Yes. So we found our skip list, or we found our value in our skip list, and this gives us a faster runtime depending on the height of your skip list. So we have, it's depending on how you code it up, if I'm gonna be honest. I was actually like, when he was talking about it, I was thinking about like, why doesn't anybody just do a skip list where this is value 1, and then over here is like, you know, a really tall one, and this is like value 1000, and then all like you basically like code it up where like, you know, it increments by 10 each time, and you just have like decimal values. But then I figured out that it's probably not the best idea to do that.
Isn't that just like making something order n?
Yeah, that's what I was thinking in my head, and I was like, wait a minute, that makes no sense. Oh, but yeah, you'd literally make it order n on purpose, which would be ridiculous.
I'm down. I have no qualms with order n.
You and your qualmless order n's. What if he grades us on like how effectively we can not order n things?
I'll write him a very stern letter. Very angry email, disgruntled email.
Disgruntled emails.
From temp email.
You know, if I was a professor, I'd keep those and frame it. Be like, yes, I ruined this boy's future. I mean, what? No, that's not what happened. Okay, yeah, so we have that. So yeah, it's the runtime is determined on the height. And if you look at the skip list, it's log n, because it's a bit like a binary search tree. It's just it's slightly different. With the binary search tree, it's just a different format of how you organize things. But since it's order H, it takes to insert and find things. It's going to be log n. And then you also have, so basically everything is log n if you're going to skip list, except for the worst case scenario is order n. It basically means that either you had a horrible skip list, or it's that one value, like let's say for instance you inserted a 1001, and it's right here, right? And then every other value has like a height taller than it. So you have to go through the entire list to get to that one value, and that's how it comes up to order n. Space complexity is also order n, because you don't know. Oh no, space complexity is n log n. Oh yeah, that's right, because you have your height and the values that you put in to worry about. So you have worse spatial complexity. That's interesting. Okay. and you have a binary search tree. It's, it's weird. It's the same as a binary search tree. I feel like there's no advantage to a skip list as opposed to a binary search tree.
Gotta be.
I mean, as far as spatial complexity and time complexity, there's no real. Your average case is going to be log of n on both, and your worst case scenario is still O of n. You don't limit it to a better worst case scenario, and your spatial complexity on skip list is worse because you have your H to worry about. Not all hash tables.
That's like 1 bit though, or 4 bit.
What do you mean?
Or not? I don't know.
No, I mean like when you're talking about bits, what do you mean?
I don't really understand his spatial complexity questions. What does that really mean? Like how much memory is taken up?
Yeah.
Yeah.
So,
The height factor of the thing.
Mm-hmm.
It's not even that much space to include one integer in a class, right?
Well, it depends. Like, if you're thinking about it in terms of like today's day and age and stuff like that, you're really not gonna worry too much about spatial complexity. But like think about it like so with this, you have okay. I can't draw a straight line for life. Okay, so you have your list, right? And you have your pointer. Well, it's not a pointer in Java, but it's like the value that points to something.
Right.
And you have your order age. But that is always a value. And the way that he said it, I think he said that there was a certain way that Java held values that pointed, in the linked list, that would, it's bigger than C. Because in C, it would be like your pointer value, you can assign it as it's a pointer value. So it's like, an int value.
Right.
But with this one, note all dash shades are different sizes. Some modern materials. Oh, okay. Well, so technically it would be bigger because what you're doing is you have let's say for instance you have a value like 6 in here, right? Or you have a value 6 in here.
Yeah.
Right. This is your value. You actually have an entire another block is what I'm imagining of space just to point to that next value, because this 6 as a linked list is pointing to 7, while this list at 6 is pointing to 13. Right? So that this entire block is taking up that much space, which is why it's n log n.
Right.
I'm sorry, what was the question again? I feel like I didn't answer the question effectively.
I don't think it matters. It's just difference between C and Java.
Okay. Yeah, that is true. It is pretty much the difference between C and Java. But yeah, the one thing that I think is weird is that with skip list, there's not a real benefit that I can see. In fact, skip list is slightly worse than a binary search tree. The only thing that I could think of would be if you have a binary search tree like no, I can't really think of anything. Oh wait. Okay, so if you have like a list that for a fact will always increase, right? So let's say, for instance, you start out with like 2, right? And then you're inputting something that's always increasing. 4, 6, 8. This is just a linked list. It's order n. That's it. But if you put it into a skip list, you know that you can add towers into your skip list. And since you can add towers into your skip list, whenever you're trying to search, you can bypass a lot of different values. And even though you're taking up more space, it's on average is going to be faster than this kind of binary search tree. So I can understand why people would do that.
Be equal on it.
No. Because like, okay, so let's say for instance we have 2, 4, 6, 8 right here, right? But and then we do it on the skip list side. 2, 4,
The
6.
height for 2, 4, 6, 8 on the skip list, is it going to be 0, 1, 2, 3, 4?
Technically, you can make it anything that you want. It's all dependent on how you organize your skip list. The way that he did it in class was like, okay, well, if I have n things, I want to do n divided by 2 at level 2. So if it's n divided by 2 at level 2, we're going to have this, and actually, no, it was this one and this one, right, is how he had it. So now we have, like, let's say, for instance, if we want to search for this one, then we have a direct line to that instead of going through and traversing through all these. And if we have it bigger,
Oh, okay, I get it now. So if you have more, yeah, that's what that picture is what I was imagining.
exactly. So I think, yeah, it's always sorted. So if you know that your values are going to be sorted, then a skip list would probably be better to access.
Yeah.
It's a better chance of having a faster access time. Insertion time is the same.
Makes sense to me.
Okay. Did you have any other questions about anything else? Is that it?
Hey, wait, one last thing. Do you guys go over treeps already?
Oh, I can put it out actually.
Man.
I was just hoping they weren't going to be on the test. Is what's going
Yeah,
on.
okay. Well, look,
No
I'm
way.
pretty sure Pokeballs and skip lists are pretty important in this class.
Listen, he has not talked about muffins once, and I am very upset. I wish that there were more muffins. If he's going to see this later, and he's going to be like, man, I should talk about, yes, you should talk more about muffins.
You gonna write an email about it?
I'll write an angry email about the muffins. And I actually was thinking about it. I was like, man, I miss your muffin talks. Whatever happened? Like, okay, so in discrete, like in the very beginning when you're learning about, like, you know, the set of all muffins, right? That's this like thing, right? After that class, I immediately went to like Alafaya and, you know, Sweet by Miss Holly, because he's talking about cupcakes all the time. I was like, man, I really want some cupcakes. And I went and I got like these 4 little mini cupcakes. And then I took a picture of it and I was like, you see what you've done? Now I'm going to gain weight. The freshman 15 is real. I hope you're happy.
Oh, dang.
Yeah, okay, so treats. Actually, I think I need to go over this too. This one is...
Yeah, the dang Pokeball is really just screwing me over.
Well, it's... I want to say that it's like, okay, so you have this value. And it's a Pokeball. And whatever value that it is, you have a secondary value that is... How is that defined? I forgot.
It's not the urgency, but it's like the hierarchy.
There's a special way that it's defined.
It's randomly generated.
Priority.
Is it randomly generated?
Yeah. The second part's randomly generated.
Okay. And it goes based off of the tree. Okay. Background min heaps. Structural property heaps are complete binary trees. As each node has at most 2 children, level that, yeah. Tree insertion. Insert value BST style. Assign a random and preferably unique priority to the new node. While the new node's priority is smaller than its parent node's priority, perform tree rotations to restore heapness while preserving BST-ness. Okay. All right. So if the new node C is the right child of parent P, perform a left rotation. Take care of any orphans. The former left child of C becomes a new right child of P. Take it back to step 3. Otherwise, if the new node C is the left child of parent P, perform a right rotation at the parent node, thus rotating the child and the parent down. C moves up to take P's place, and P is now the right child of C. Tree deletion. Okay. Expected height and empirical analysis. Oh, like the Pokeballs. Oh, no, wait. These are just practice exam problems. Okay. If I had Microsoft Edge, I would do it. Insert the value 20 into the following tree. Assume the node is randomly assigned at priority 10. Okay, so we have, let's do this. Eight 12. Three 18. 190. 644. 547. 4016. Okay. And then we want to, assuming the node is randomly assigned priority 10. Okay. So what we want to do is 20, 10, inserted. Okay. So okay. Insert the value BST style. It is inserted as a new leaf node. Okay. So we have 2010, and we're going at the top. The value at the top is what we want to preserve. So we have 8, 3, 6, 5. Wait, no, I'm sorry. 8. It's bigger than 8. So we go 40. It's smaller than 40. So it's going to go here. 2010. Okay, but then we have a conflict because we also have to follow the priority, and the priority is not random. Yeah, well, a new node's priority is smaller than. While a new node's priority is smaller than the parent node's priority, perform tree rotations to restore treepness while preserving BST-ness. Okay, so this one, 16, is smaller than 10, but it should be to the left of here. So we want to, oh, this is going to be super confusing. Okay, so we want to do a pull because we want the 10 to be up here, and then the 12 to be down. So somebody help me out with the BST. If you're looking at the bottom values, how would that be arranged? Because like what you're doing is you have with the BST you have the conflict, and whatever the conflict is, you pull that one up, right? Because and all the lines dangle, and they stay the same. So if you're doing that, while preserving BST-ness. Okay, so what we have to do is perform a left rotation at the parent node. Okay, so the left rotation at the parent node, thus rotating the child up and the parent down. C moves up to take P's place, and now P is the left child of C. Okay, so we want to rotate these. And this one becomes an orphan. So what happens to orphans? Take care of any orphans. The former left child of C becomes the new right child of P. C moves up to take P's place. And P is now the left child of C. But if it's the left child, that makes no sense. Okay. Somebody want to help me out here? Like,
Telling you, man, these Pokeballs really just.
1020 go where 4016 was, and 4016 go down as right child of 2010. Oh, okay, so you have to do that one first.
I wish he had the PowerPoint up. I don't know why he doesn't have a PowerPoint for this.
Okay, so yeah, this one switches, right? Right rotation. Right rotation 2010 go to where 4016 was, and 46 go down as a right child of 2010. So this one, so if we do, so this one goes here. So it's 8. That's not an 8. 8, 12. And dealing with this one over here. 20, 10. And then as the right child, 40, 16. Twinton, okay, right child of Twinton, yes. Thank you, 1111111. 3018. And then let's assume that we have that. But since 12 and 10 are not in its place, we still have to switch it out, because we're assuming the priority has to be matching as well. So what we would do is we would do a left rotation. No. Wait. Yeah, maybe. That one. Well, the new priority is smaller than the parent node's priority. Perform true rotations towards short. Perform left rotation at the parent node, thus rotating the child up and the parent down. Okay, so this one is going to go like this. It's going to be 20, 10, up here. No.
Robot has it on his screen.
Oh, he does. Hey. Here, let's present that. Present to everyone. Okay, so you have 4016, 2010 down. Eight 12, 13 9. Okay, but okay then that works. So what you did is that so we have the 812 and that rotates down, and that still preserves everything below the node, and so 2010 becomes our new parent node, or I'm sorry, our new root, as it were. Which this is the root, so it's 2010, 2010, 4016, 318. No, I'm sorry. 812. Thank you, robot. 318. And then so on and so forth. So that part doesn't change. Johnny's back. Oh, wait. Got presented. Okay. So then so it looks kind of like this.
Can you like zoom out of that, or is this like the smallest you can?
Oh no, I can. I just have to rewrite it.
Oh, okay.
Yeah, OneNote is fantastic. So essentially, it looks like this. And the way that we got there is SQL is running. There we go. The way that we got there is we inserted first, so we had 812 up top, and then we inserted here, right? And then it was at the end. So we rotated these two, and then we pulled this one up, right?
Nice, gotcha.
if I'm not mistaken. Yeah, as far as I know. And deletion. Find the node with the value to be deleted. Search for BST style. While the node to be deleted is not a leaf node, while the node is deleted is not a leaf node, if the node to be deleted P is exactly one child, rotate P down the opposite direction of its sole child. C moves up P's place. Take care of any orphans. Repeat back to step 2. If the node to be deleted has 2 children, then let C be the child of minimum priority and do the following. Rotate P down in the opposite direction. Okay. Delete the following value from the following tree. Well, let's just see what happens. 12, 8. $739. $60.14. $5.40. $8.53. $10.60. $9.71. That looks right. Okay. And then we want to delete the value 12. Okay. So we delete the value 12. And let's find out what happens. Because we do have 2 children, and that's a problem. Well, the node is not a leaf node. If the node is to be deleted that has exactly 1 child, that's not the case. If the node to be deleted has 2 children, then let C be the child with the minimum priority and do the following. Okay, so the minimum priority is going to be this one. Rotate P down the opposite direction of C. Rotate P down the opposite direction of C, so C moves up to take P's place. Okay. So these switch. So 60, 14, 12, 8, 7, 39, and then we have 2 of those, and I'll write them if it comes up. Okay, and so now take care of any orphans and repeat back to step 2, right? So now it is a leaf node, so we want to go ahead and delete it. So that one's done. But now we have a conflict because no, we're fine. 14, 39, 53. Wait, why is that right? Isn't the priority supposed to be, what are the rule on the priorities? Hold on.
No, you're right. Oh, wait, go back.
Yeah. So look, right, so we have 12 and 8. Okay. That's what we want to delete. We switch those out with the rightmost child, right? That switches out. So this now is 60. Oh, okay, so 60 up top. I'm sorry, I completely forgot about that.
The location is the opposite way.
Oh, here we go. Present to everyone. Okay. Wait, so we want to rotate it that way?
Yeah.
No. Whoa, wait, no, because
And then you rotate the other, and then do this.
Wait, what?
And now you can delete the 12.
Why
No.
can't you just do it the way that Raphael did it?
Yeah,
You have to rotate a certain way. You can't just like
No, but
switch them. You have to rotate them.
Zemlansky said that you have to rotate it the way that has higher priority. I thought what I wrote in my notes was you rotate according to higher priority.
It's online. It says opposite direction of C.
Rotate P down in the opposite direction of C. So no. That is then in that case he's right. So instead of I can't do it this way. I can't. If I'm rotating down, what I'd be doing instead of doing like a swap,
Yeah, you just switch them. Yeah.
what I would do is I would do this,
Oh, I got you.
right? Because I'm rotating. I'm not
Yeah.
actually.
Swap.
And then
Yeah.
Okay.
so yeah,
Now
60.
you can rotate them again. Yeah.
And then I would rotate. Then I would rotate it again. That way 60 is here, and then 12 is here. No, wait.
No, you would push the
No.
12 down, and the third node would become
Yeah.
the second node.
Okay, hold on. So we have. Let me go back.
Okay, that makes sense.
12, 18. That one. That one gets pushed down, right? So you have 60 here. That's 14. And then you push it down again. And it's like this. 7, 39.
Yep.
Okay. And then you rotate it one more time. Right? So, okay, so it goes 60, and then 12. No, I'm sorry, 67, and then 12.
And now you can delete as well.
And then what happens is that then you can delete the 12, and then all this other, well, so like wherever the 7 came from. Okay, so he's got like a bunch of other people on there. Now we can delete the 12 because that's in the regular node, and then whatever's going on with the 5. What about the lower ones on the bottom, below 7? Right. So
It stays the same.
They stay the same. So we have 540. And then over here, 853 as well.
Yep.
Okay. And then you have 1060 and then 971. 10 and 9. All that stuff. Okay. That's confusing. Stop presenting. Yeah, that's crazy. But I think I understand. Like basically, it's you have to follow this kind of rule. And then once the node is deleted, it has reached the node position, obliterate completely, goodbye leak node. Okay, cool. That works. Centigrok. Okay. Just for kicks, don't know why T extends comparable T. Oh, okay. So it extend like as opposed to implements?
It's just, why do you have to put the extra T? Why can't you just do T extends comparable?
Because it throws warnings in your face. No, from what my IDE has told me, what ends up right, it will throw exit warnings if you do that. But what you're doing is when you're saying comparable T, that is your definition for that specific class of what you want your generic value to be. So for example, if you're doing like any type, because he did any type for like a bunch of his stuff, right? He was like any type Bob is our variable, and any type can be anything. It can be an integer, it can be strings, it can be doubles, it can be whatever you want. whatever you're putting in here, right? If you say extends comparable, right, without that T there, or without any type, it doesn't actually know what the value is. Or like whatever you're extending. So for example, it's your public class. Public class foo. Right, extends comparable. It has no idea what value under, like inside these brackets, dot, 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 will need to extend comparable. Right? So if you put like, you know, any type or T there, then it's like, oh, well, if I see a T and I see T Bob, then that's what I can compare. That's going to be my generic. That can be any value. If it's not there, then it'll throw exit warnings or even throw an error. But yeah, that's my 2 cents. Does anybody want to go over anything else? I don't see a show of hands. No. Because if I'm gonna be honest, like I'm almost done. I've got like a class in the morning, and then I have like a long break, and then I'll take the test, and hopefully we all do fantastic. Ooh, did they give answers to the data structure review during lab? Yes, I actually have it somewhere. The data structure review is like the handout that we were given, correct?
Yeah, correct.
Okay. So yeah, I actually have all of them. Cool. Okay, I definitely have to work with this. Any specific answer that you needed, or any reasoning?
No, it was more of just checking work kind of thing, and I figured they give the answers, and since he normally does not give answers,
Oh, okay.
that'd be a good thing to have. Could you, like, if I sent you my phone number, could you take a picture of them and just text them to me?
Yeah, sure.
All right, awesome.
Let's see why not. Yeah, it's really it's not that bad. The only thing that I would have a problem with is stacks and queues, because I'm not very good with stacks and queues. That's actually one thing that I'm worried that he'll put on the test, because he did mention it in the very, like, you know, with skip lists, like at the end. And I feel like he's just going to be like, there you go. Here's some stacks and queues for you. Here's some CS1. Why not? But aside from that, like, I think I'm okay with how.
What is the answer for 1F?
1F?
Is it dirty bit?
Yeah, it's the dirty bit. So
What is dirty bit again?
the dirty bit?
Yeah.
It's a song. It's great. When you're using quadratic probing, do we delete an element from the hash table? How do we delete an element from the hash table? So when you're removing an element from the hash table, I do believe that when you're doing the quadratic probing, you leave something there to tag yourself when you're going into the function. If anybody else can explain dirty bit better, that would be fantastic.
I got you. All right. So what happens is you're going through the cases, even in linear also works. So let's say you say something in 1, you say something in 1. Oh, nope, there's something there. 2. Save something in 1. Nope, 2. Nope, 3. So basically you've saved something in 1, 2, and 3. Now if you delete something in 2 and you're trying to look for the value in 3, you'll never find it, because you'd go through 1 and say, oh, it's not there. You go through 2 and say, oh, there's nothing there, so we can stop. And you'll always stop before you hit 3.
Okay.
That's actually a better way to what I was going to do. But yeah, Did you have any other questions? One.
No. The best case for the AVL tree deletion is order 1, right?
the best case scenario for the AVL tree is
Yeah.
is order 1, correct?
Okay.
Yeah, best case is order 1 for insertion. Deletion is order n, or I'm sorry, log n, and worst case is order n for everything, and average case is log n for everything. That is true. Okay.
Sorry, when is the best case order n for deletion?
No, sorry.
I think it's order 1.
This is for BST.
No,
I'm
for
looking
AVL.
at the thing. So if is there an AVL one here? I don't think so. Self-balancing trees. Yeah. Okay. So there actually wasn't a question for best case for deletion, but I'm going to assume that it's log n, because when you're doing a deletion of an AVL tree, you're going through the entire tree. Not the entire tree. I'm sorry. You're going through the height of the tree to get through it.
No,
And
but for the best case, if you just if the one that you want to delete is in the root node, so you can just delete. I mean, pick that one and then rotate it down and then delete it, right? So it's order 1. Is it?
For an AVL tree?
Yeah.
So what you're saying? Okay. So essentially, so you have a balanced AVL tree, right?
Mhm.
Blah 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 blah. Best case scenario
So the root.
would be the root.
Yeah.
So it's order 1. Yeah.
Yeah. Okay.
Your average case would be order H.
Log n. Yeah, or order H.
Order H, or 2 to the n minus, or 2 to the n minus 1, I think. No, I'm sorry, 2 to the n. Yeah, it's 2 to the n. So it's how many nodes do you have, which also comes out to log n, essentially. Yeah, and then your worst case is for deletion is log n as well.
Mhm. Okay.
Because I'm sorry, your worst case is order n. My apologies. Because you have a list that devolves into a linked list.
That is BST.
That is BST. So AVL theoretically cannot devolve into a linked list because of the way that AVL works, unless it's just a sorted array of values that are forever increasing. But then no, because then it would automatically sort itself. It's self-sorting. So you'd always have log of n.
Yep.
So once the AVL tree is sorted, then deletion is log of n, insertion is log of n. It's all log of n. Yeah. Self-balancing trees, heaps. Yeah. Heap operations always order 1. Stacks and queues and linked lists. You think you'll have stacks and queues on the test? I don't know. He might not.
Maybe a coding thing.
But a coding thing would be awful.
You'll just be like, implement a pop method, implement a push method.
Oh, okay. And yeah, that's fine.
Write the entire queue, please.
Everything right now. That would be fantastic. Oh man. Wait, did they give the answer? Yeah. So yeah, I can Johnny, I can go ahead and text it to you. They didn't necessarily give the answers. We just worked on them conceptually, and I don't know if there's an answer for if they had an answer key. They usually don't have an answer key. But oh no, wait. But they did check it in lab. Data structure review. Preparation for exam 1. Let's see. Oh, well, yeah. Yeah, he did check it before we got out, and then he said everything was okay. So I would assume that everything was okay. Thing. Data structure review, skip lists, creeps, random BSTs. Oh, okay. I see. Bloom filters, 2-4 trees, AVL trees, binary search trees, hash tables, hash set and hash map, algorithm analysis and design, empirical runtime analysis. I think we went through everything. Yay! Okay. Sweet. Any other questions? Can I get it as well? Yeah, definitely. I'll definitely send it to you. I'll just send a mass text message. All right. So that's that. I'll text you guys. I'm gonna go to bed.
Is anyone planning to meet up tomorrow before class?
What time?
I know, like I'm free anytime before class.
Okay. I mean, I get out of my my linear algebra class at 12. So
We can meet after that if you know,
yeah, definitely.
maybe like last minute stuff.
Yeah, no, I'm done. Oh, who's this? Super. Hey, Super. We're any good with summations? Yeah. Like if I'm gonna be, I'll probably work on them a little bit more. Before I get to my linear algebra class. That way I'm like more in depth with it. I think it's honestly just remembering the formulas that I have. And then like just kind of like algebraically solving for everything. You know. But yeah. Anything else? Any other questions? Comments, concerns? All right. Well, I'm out of here, guys. Good luck. Which dude? The guy that joined in the dark. Well, he wasn't screaming, so I think we're okay. All right, guys. I'll see you guys later.